So when we have things like piecewise functions, we can't always take the limit or the tangent of every part of the, we can't take a picture, sorry. We can't draw a tangent of every part of the picture because there's holes in our picture. For example, here's a piecewise function. We are going to do a little sketch on the side of our sheet. So here, let's do 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. If x is less than 1, then the equation gives me x squared. What's the shape of x squared? Parabola. Parabola starts at 0, 0. I'm going to do the left side first because it's less than 1. 1, 1, 2, 4. And so I have something that looks like this. Notice that I have an equal here. So it's an inclusive restriction. So when I go to the right, the point 1, 1 is an included circle. So this is a solid parabola with an inclusive endpoint at 1, 1. Now, the next part of my graph is a line starting at 1, but it's exclusive to 1. Can you rewrite this in mx plus b form? Negative x plus 3, just for your brains to see what's the m and what's the intercept. The intercept here is at positive 3, and then we're going down 1 left one, sorry, down 1 right 1. So in theory, it's going to start up here and go down 1. Pardon me? The slope is down, but our intercept is up, right? And then we're going to be here. So that's an open circle. Oh, sorry, that one's going to be an included circle. Something like this. I use open circles to identify kind of where I'm starting just so I can do my sketch. But realistically, this is my graph without that upper circle there. So you can see that I have a jump here. We call this when there's a split in the graph, a point, not a point, sorry. Yeah, it's a discontinuous point where I have a jump spot. So I have a value for x at every point. My domain is x is all reals. My range is x is all reals, but I cannot take a tangent at all the points. But I can say what is the derivative from the left of a key point and what is the derivative from the right. And it's going to be the same process that we did before. So if I'm looking at the value, we're going to just look at what is the function at a particular point. From the left, we want here x is less than 1, and we want our value to be f of x. From the right, we want x to be greater than 1, and what is the value of f of x? Okay, in this case, f of x is x squared, and in this case, it's 3 minus x. So let us approach from the left, 0.9, 0.99, 0.999. And then from the right, 1.1, 1.01, 1.001. Okay, so I'm just going to check this into my calculator. Clear everything. If you do second mode, it gives you the quit function, which just puts you back to the home page. So 0.9 squared, 81. 0.99 squared, 0.999 squared. Oops, squared. Okay, so here is the function that I get. So let's write that down. 0.81, 0.980, 0.998001. So we say that as x approaches 1 from the left, f of x approaches 1. So again, the way that we write this in mathematical notation, the limit as x approaches 1 from the left, not negative 1, the little symbol, you write it in place of an exponent. That tells you the direction, left of right. The limit as x approaches 1 of f of x equals 1. Now I'm going to do the same thing, but from the right. I'm going to say 3 minus 1.1. 3 minus 1.01. 3 minus 1.001. Okay, that's our numbers here. So I'm going to write that in. I go from 1.9 to 1.99 to 1.999. So this is telling me from the right, as x approaches the number 1, my y values approach the number 2. So again, I have to make a mathematical statement here. The limit as x approaches 1 from the right, so starting with bigger numbers, of f of x approaches 2. So this is what we call a, yes, I'm getting to that point, but yes. This is what we called a left-hand limit, and this is a right-hand limit. Because these two do not match, then our statement is that the limit as x approaches 1, if I don't specify a direction, that means I'm meaning from both sides. If the two sides don't agree, then the limit as x approaches 1 does not exist. Okay, if the left and the right-hand side do not agree, then the limit doesn't exist. You can ask, does the left side exist? Yes, it does. Does the right side exist? Yes, it does. But together, they do not work. Okay, so this box, and anytime you see a box from here on out, commit it to memory. Okay, the general limit as x approaches a equals L, whatever the number is. L just represents a number. It only exists if and only if from the left you get L and from the right you get L. Okay, also in math notation, this is how you abbreviate this sentence or this part of the sentence. Okay, so the limit exists. You can say it this way. The limit exists if and only if the LHL equals the RHL. That's another way you can put it in shorthand. Very important that the two sides match. All right, let's take a look at an example where the graph is already given to us. Here is a graph. Please take note of the jumps and the points of discontinuity. You can see where there are points of discontinuity. However, notice that in this case, a point in the hole exists. It's just not where you expect it to be. Okay, so now by observation, the limit as x approaches g of x from the left side. So I'm going to go find the number 2. Here it is. And from the left side, what number am I approaching? 3. And from the right side, what number am I approaching? 1. Okay, so then the overall limit does not exist. Okay, now let's look at the number 5 right here. As I approach the number 5 from the left, what number am I approaching? 2. as I approach 5 from the right. What number am I approaching? 2. What's the limit? 2. What's the point? 1. Okay, so it is possible for your limit not to approach the same point as your function, as long as the left and right side agree. At the actual point, it doesn't actually have to agree. Does that make sense? Okay, so as long as the left and right agree, even though g of 5 equals 1, at that single point, and every other point they converge at 2, so the limit exists and it is at 2. Okay. Exactly. And that's why yesterday I said we don't cancel, because we're not worried about the point. We are kind of worried about the point of discontinuity, but we are worried about what does it look like as we get closer rather than right at that point. Yes?
That had like a cancellation thing that kind of mess me up like after.
Yes, we can go over that in a minute. Okay, let's look at a absolute value. What does the absolute value graph look like? It's a V centered at 0, 0. Okay. Now, in example 3, it says the limit as x approaches 0 of the absolute value. So, is that true? Yes, it is. As we move to the left and as we move to the right, they are both getting closer and closer to the value 0. So this is just a visual demonstration here. Right? We can see that it approaches 0. So the left-hand side and the right-hand side, oops, that was supposed to be an R, agree. So therefore the limit exists. Okay, now let's do a piecewise function without drawing the picture. Determine whether or not it exists as we approach -1, and as we approach +1. So we're looking at 2 different limits. So first let's take a look at as x approach -1. So I'm going to look at the limit as x approaches -1 from the left. What is the limit as x approaches -1 from the right? So the direction is a sign and the exponent spot, so don't get those guys confused. As it approaches -1 from the left, what equation am I focusing on? The first one. So I'm looking at -x minus 2. Okay, do some calculator, or you can even do this in mental math. If I'm at -2, -1.5, -1.1, what number are we approaching? -1. Right. And the other way that you could do this is by inspection here. X is allowed to equal -1. And because I don't have a denominator, I could cheat a little bit and just stick -1 in there. Negative times -1 is +1. 1 minus 2 is -1. So that's okay. As I approach -1 from the right, what equation am I using? X. So as x gets closer to -1, what is x? -1. Okay, so in this case, we have an agreement, even though we use different equations. So the limit as x approaches -1 in general of this function, we have an agreement that the limit is -1. Yes, sir. I'm not worried about the third one because the third one is nowhere near my point. I'm only looking at the direction from left and right of that point. And the third equation is after +1, and I'm at -1. So it's nowhere near me. I don't have to worry about it. Any other questions? Yes. What happens if I use, oh, from the right? This one here? Well, think of it this way. I start at -2. -2 is -2. There's no equation here. So whatever number I put in is the number I put in. So as x gets smaller, from -2 approaching -1, I don't have to change anything about the number. So I can just say from -2, I'm just going to get closer to -1. So the limit as I get closer and closer is -1 because I don't have to change any of the functions. Right? Okay. All right. Let's take a look at the other side. So I'm going to do this one in different color. Approaching +1. So let's take a look. Approaching +1 from the left. What equation am I using? So I am less than +1. X. As x gets closer to 1, what's x? 1. Okay, so limit as x approaches +1 from the right. Now is where I use my third equation, x² minus 2x. I'm allowed to equal +1 in that third equation, so I could just cheat here, again, because I don't have a denominator to worry about. I could just put 1 in there, and what is it going to give me? -1. I do not have an agreement here. So the limit as x approaches +1 in this function does not exist. And therefore, the entire, sorry, this one was a right side. Therefore, the whole limit does not exist either. Okay, any questions about that example? Right with that? No? Tell me. Oh, I see. I just put it 1 in here. Yeah. So 1 squared is 1 minus 2 is -1. Yeah. Yes. Say that again. Oh, because I'm just dyslexic. Because the left side and the right side exist, yes? However, the left side does not equal the right side, therefore the general limit does not exist for that point. Sorry for the confusion. Any other clarifying questions? Yes. Okay, let me draw a picture. I think the picture helps. This tells me I have a line that starts at -2 and goes down. So let's just pretend this is it. This line only exists up until x is -1. So somewhere here, there's a cutoff. So this line exists like that. The middle line exists between -1 and 1 exclusively. So there's a circle like this. And then the third equation, x² minus 2x, x and x minus 2 has something like this. So when I'm interested in what is the limit at -1, only those two are important. The third one, the restriction is that it's greater than 1. So it doesn't affect the graph at the point -1. So when you have a piecewise function, you're only worried about the two equations on the left and the right of the point you're interested in. This one has no effect on what's going on at that point. So I don't have to worry about it. Any other questions? Okay, let's do one more example. Okay, anybody remember what 1 over x squared graph looks like? That's not totally wrong. You're on the right track. Yes? You're on the right track. I've heard 2 things that are on the right track. Yes, a reflection on the y-axis. Perfect. Okay, so this is 1 over x squared. We did this like day 2, I think, of our course. And just as a reminder, this shape is 1 over x. So when we square it, all negatives become positives, which is why we have a reflection over the y-axis instead of the instead of kitty corner, essentially. Okay, so this is the function that we are dealing with. We want to know is what does the limit as x approach 0 exist? So we want to look at approaching 0 from the left, approaching 0 from the right, and your f value is going to be 1 over x squared. 1 over x squared. So again, from the left, 0.1, 0.001, 0.0001, extra 0 there. I'm going to give you a tip here. I'm hoping that you can see that as x gets closer and closer to 0, when we have a denominator that gets very, very small, what does the value of the fraction become? It becomes very, very big, right? So this will go off to infinity. This is why we can't divide by 0, because infinity isn't a number, right? And you can see from the picture as well. As we get close to 0, our graph is taking off to infinity forever and ever. Okay? And the opposite is also true. Let's approach from the other side. Sorry, these were supposed to be negative numbers because it's on the left side, but the positive numbers are going to do the same thing. 0.001, 0.00001, da 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 da. This is going to closer to 0. This is going to do exactly the same thing, off to infinity, right? Because these negative numbers are all getting squared, so they're going to be positive. So the positive numbers squared are going to give you the same result. So as we are approaching 0, our graph from the left and right is going off to infinity. Make some space here for my writing. So notice that the values of f of x can be made. Does anybody know what this word is? Arbitrarily. Yeah. Means it doesn't really matter the value. You're just taking a large number or a small number. Close enough. As large as needed, yes. To 0. So the values of f of x do not approach a number. So therefore, you guys know that the 3 circles mean therefore?
Yeah.
In case you didn't. Therefore, we say that as the limits, x approaches 0, the limit of 1 over x is infinite or does not exist. And I want you to think about why this is true. What happens to your slope if you have a vertical line?
It doesn't have a.
Doesn't have a run. You have a 0 in the denominator, therefore it's technically infinity. So this is kind of like the trend here that we're seeing, right? This is essentially the derivative of slope. How do we define slope? How do we use slope? All right. So if you have a limit that is going off into infinity, we say that it goes off to infinity or it doesn't exist. Either is acceptable. Yep. So either is fine. Either way you say it is fine. Okay. So in general, if it is defined on both sides of A, so of your key point, except possibly right at A, right? Because we can't say what is 1 over x squared at 0. So we can't evaluate it at A, but we can get very, very close to it. Then, sorry, if we have defined on both sides and we have a limit that goes off into infinity, that means it can be as big as you like, a million, a billion, a trillion, either way, whatever. If it's getting too gigantic, then we're going off to infinity. You can still have a limit of a very large number, as long as both sides agree to what number that is. But if it goes on, and no matter what you put in, it's going to give you a different but large number, that's when we say that it's going off to infinity. And this will happen in specific cases when we do word problems, which we will get to. Similarly, if we had an inverted graph or an upside down graph, you could also have a graph that goes off into negative infinity. So both sides of the equation are pointing down instead of pointing up. That is also a possibility. Okay, anytime you have a limit that goes off to either infinity or negative infinity, this is what we define as a vertical asymptote, because this is a point that does not have a slope. Okay, so box this. Your definition, all the different possibilities of a vertical asymptote is if we have a limit that goes off to infinity from either direction. So you can have something that goes like this, right? As x approaches 0, the right side's going to positive, the left side's going to negative, but they're both going to infinity.
But
It's D and E regardless. Infinity means does not exist. Whether they're both the same infinity or opposite sign infinity, infinity means it doesn't exist. Okay, so you could have things like we just saw going out like this, or things going down like this. These are all the different ways we can identify the infinity. As long as it's going off into the distance and beyond, we have an infinite limit, or it does not exist. Okay, I'm going to stop talking because I feel like we have the general idea here. I would like you to do the last two examples before the bell goes here. You are identifying what happens to this function as you approach 3 from the left and from the right. My suggestion to you is take this function, type it into your calculator, go to the table and just choose some small numbers. Look at the chart as x approaches 3 from the positive side. So look at 3.1. Whoops. 3.1, 3.01, 3.001, and then make a new list or clear that list, same equation, but now you have x going from the other side. So 2.9, 2.99, etc. Okay, and based on what you see, I want you to sketch the graph. Here are your options for the sketch. Okay. So take a look at that. Take a look at the 7th one. This is something I want you to do in class, and I will post the final answer as soon as you guys are done or at the bell.